Thanks, everybody. Hey, you're still here. Okay. We're going to nerd out. We're going to nerd out because you're all nerds. Today's Pi Day. Did anybody? Okay, you got that. Great. Okay, so I'm going to take you deep under the hood. We're going to look at AI fundamentals, but not just a 101 on AI. This is a different way of doing AI, a different approach to make models smarter, faster, and greener. This is all super important. What's the motivation? We're going to cover this. In fact, I'm going to skip over the agenda. We'll just go and do it. Okay. As I mentioned, 3 tracks to what we're doing: the tools, the fundamentals, and the policy. You heard about the other 2. This is about the fundamentals. The big problem with our neural networks are, compared to this 2-pound biological computer that we carry around with us that can learn and think concurrently, that's not what deep neural networks do. Deep neural networks, large language models as well, you have to train in one massive instance, release the model, and then run inference in another engine. So that's one strike against it. It's so compute intensive. We've got a portable machine we're carrying around with us. It does far more thinking than the biggest data centers filled with GPUs. And the third point is it takes so much data. A young infant can learn to recognize faces on so few samples compared to the facial recognition models that I've been training in my previous job. Millions and millions of samples are needed before the model converges and gives you a level of accuracy. So, recap from the previous summit. No, watch the video. I'm going to skip through that. Okay. I want to follow on from what Kai talked about causality. And that's my line of inquiry about, can we make neural networks that actually are not based on correlation, but based on causation? So when you look at this as an existing neural network, every node in one layer is connected to every other node in subsequent layers. It's basically saying, I mean, it's the height of intellectual laziness to say, I don't know how to solve this problem. I don't even want to think about it. I'm just going to use historical data and ground truth, and I'm just going to throw it into the model and see if it can give me answers. And the sort of the bloody-mindedness in me, I think to myself when I see a problem, I think, well, how hard could it be? You know, we're going to figure this out. Okay, so last summit I posed the question, what if each of these nodes in the neural network was instead some sort of physical element? And I chose a fluidic model. This is actually not a crazy thought. There's a whole body of research called PINs, physics-inspired neural networks. Some people call it physics-informed neural networks. I like the word inspired. Okay, so that's where we're going to dive into. And if you want to get a primer on this, if you want to get up to speed on it, Steve Brunton, who's at the University of Washington, has got a great lecture series on YouTube. Go and check out what he does there. He looks at a problem. He says, well, is that similar to some sort of physics model? Let's take the equations from that and let's go from there. Let's have the laws of physics actually determine the weights of the model, and all the other sorts of things. Okay. I had a different area of exploration. Where is Kai? Is he left? Oh, he's right there. Okay. So that what happens in Vegas, Kai, yeah, it doesn't stay in Vegas. It comes home with you and haunts your dreams. So, or sometimes they come home and they call you dad later on. Okay. Okay, but Kai and I were at an AI summit last year sometime. And he explained to me, he gave me the primer on reasoning AI, and I told him, well, I've been thinking about a different type of network, and I've been talking about, hey, I've noticed a striking similarity between quantum mechanics and artificial intelligence, between the type of network that exists in our idea of quantum theory and the networks that exist in AI. At the left-hand side, you have an input, and at the right-hand side, you have an output. And in the middle, you have kind of this cloud of probability. And you have vector math that has these affine vectors. Affine means they all sum up to 1. Okay. And they've got the same sort of throwing their hands in the air attitude, that we don't know what goes on in the middle, but in the case of Richard Feynman, shut up and calculate. Actually, not misattributed to him, but I think he espoused that same philosophy. We don't know why it works. Here's the math. Just go and do the calculations. Geoffrey Hinton, when espousing the math of deep neural networks, also says, hey, I don't know why it works. Just equivalent of shut up and calculate. Just move forward. Forward is his pivotal paper. Okay, quantum mechanics and AI wave functions. I'm considering a fluid that spins. Okay, and it's a Newtonian fluid, and I'm pondering on how can we model the velocity field around a single volume element of fluid. How does that velocity field propagate? And of course, in order to do that, I need to simplify the model, because I don't want to solve the Navier-Stokes equation. So I'm only considering orbital motion, and I'm taking a slice through a 3D model. So it's reducing a 3D model to 2D, and I'm only looking at the wavefront. So not the entire fluid in all of its glory, in its stable state. I'm looking at the wavefront that propagates that from the central volume element, and start off where the entire fluid is initially quiescent. And so when you do that, it turns out that the Navier-Stokes equations can dissolve into simple matrix math. Okay, simple arithmetic that we can do in high school. Okay. And I did that. And actually, it's not something I just did after the conversation with Kai. It's actually been something I've been working on since about 2005. Okay, so rather than bore you with the math, I'm just going to give you a simulation of it. Okay, so up it pops, and we're going to go here, and we're going to make it big or go home. Okay, so you're seeing here a spinning volume and a cloud of probability, and I started off spinning with an angular velocity of 1, and it decays almost to nothing, but then builds up again and ends up at at 1 again. Okay, that's using simplified physics. I then did it with a more exhaustive complex physics, and I end up with this. Okay, so you can't see what's going on there, because I'm going to zoom out and show it to you at that resolution. Okay, so this is interesting. And what's going on here is the spinning volume, and there's something familiar in the cloud of probability that emanates from that initial spinning volume. It looks like something we've seen in physics elsewhere. Okay. So I look at that, so the redness of it is the orbital velocity of this fluid. And because I've taken a 2D slice through it, it looks like a matrix. Okay. I know what it is because I've been studying this in physics. It is, in fact, so there's the energy view, there's the angular momentum view. But what I do now is I rotate that through 45 degrees. And I look at, let's just zero this out. I look at how the wavefront propagates in time. So this is looking at one lobe. The wavefront propagates in time, and it moves along and then reaches 1 again here. So I don't know what to make of this. I think it is the observable at either ends, and the middle part is a probability field. And so this is the amazing thing is, I'm gonna kill that, and we go back to the presentation, and I'm going to just wrap up here, where we talk about exactly what the implications are. Okay, so the results are you get these 2 lobes propagating from this flowing volume element, one going off at 45, the other going off at minus 45 degrees. Well, because it's a slice through a 3D volume, it's actually representing a vortex, and it's actually 2 lobes of a vortex. The momentum and the energy build up on the wavefront. Okay, so in the full slice through the entire 3D model, it looks like that. Looks very familiar. Looks like the sort of clouds that you get around an electron or something like that. And it turns out that is in fact what it is. This is all built on a separate thought experiment in physics around fluidic space-time. So, but what is the application for deep neural networks? What does it mean? It means that you've now got a physics that can determine the value of the weights. You don't have to learn them. I mean, that's the whole point of PINs, of physics-inspired neural networks. But this type of neural network, because it's a causal neural network based on physics and only based on local interactions, where one volume element is engaged with the adjacent elements only by the contact surface, it means that you've got a dramatic drop in computation complexity to compute the network and how the network evolves. You only need to look at 2 adjacent nodes in the next layer. So you reduce the order of complexity to order n rather than order n squared. In a deep neural network of today's logic, let's say you've got 1,000 nodes in one layer, 1,000 nodes in the subsequent layer, you'll have 1,000,000 connections between them, so 1,000,000 weights. This one, you'll have n weights. It turns out you actually only have 2 weights, and you run them down. So if I was to build this in a chip, I'd have 1 register, and then a register for the next layer, and I'd run that processor down there doing simple multiplies and accumulates, only 2 and 1 add to get each element, run it down, and then load the result back into the first register. So what does it mean? Well, we can ask our AI, what does it mean? Actually, if you ask her what is a fluidic model, she'll quote from the RAG data we gave her, the script from the last summit. How do we train it? Well, I don't think we do train it, because the weights are based on physics. But how do we pose problems to it? I don't know. It's almost as if, I don't know, I've stumbled across an abacus and I don't know how to ask it questions. So that's the area of where we're going. Look, next steps are, there's still math I need to do. I need to normalize the matrix math. I think I know how to do that. I'd really love help in simulating this. It's a rotating field. Love to animate that. Love to run some experiments. I'd love to explore the implications of that network actually being a qubit, and explore the behavior of a fluidic neural network. So that's part of what we're doing. On the area of physics, this is actually the fluidic space-time actually unifies quantum mechanics and gravity, but I'm more in the line of the Grinch, where he said, solve world hunger and tell no one. Maybe I'll do that. I've already got a ban on Reddit for talking about this. So the physics community, I'm not as open as the computer science community to new ideas. But hey, why not join Quai, join the Fundamental AI Research Group, and we can do this stuff, and we can do some exciting things. Okay, thanks very much. I hope we've caught up some time. Thanks.